So now that we have some background on stability of alkenes and structure of alkenes, let's talk about what the two possible mechanisms are. So just like with nucleophilic substitution, there are going to be two possible mechanisms. There can be a concerted mechanism, and there can be a stepwise mechanism. So let's take an example. Okay, I have this T-butyl bromide reacting with hydroxide. Remember, here's the alpha position here, so I need to take off a hydrogen from a beta position. The hydroxide can come in and grab a proton from the beta position. The electron pair can come over here to form a new pi bond and push the bromide off in a concerted mechanism. Okay, so if I look what's left, there's a CH3 here, a CH3 here, and a double bonded CH2 up here. CH3, CH3, and here's my double bonded CH2. If you want to keep balancing, you've also got water plus Br minus. So if I was going to name that reaction, this is an elimination reaction. And we can name it the same way we named nucleophilic substitutions. So are there two molecules involved in the rate determining step, or is there just one molecule involved? Well, there's two. The hydroxide is involved, and the alkyl halide is involved. So this is an elimination bimolecular, or E2. You can also draw a rate equation for this reaction then. Rate equals K times both the alkyl halide and the base. What about a stepwise version? So I'll draw the exact same reaction, and we'll draw a stepwise version. So in the stepwise version, we have the same thing that's going to happen that happened last time, and that is that our halogen has to leave first. So if our halogen leaves first, that leaves a carbocation intermediate behind, which can then be deprotonated by our hydroxide. And this electron pair comes over here to get rid of our positive charge by forming a new pi bond. Plus H2O plus Br minus. So this is again an elimination reaction. I start here, and I lose HBr to get to my product. So this is an elimination. And again, which step is going to be the rate determining step? Is it going to be slower to go from a neutral molecule to two charged species? Or is it going to be slower to go from the charged things back to a neutral molecule? So just like with nucleophilic substitution reactions, the first step is the slow step. So what molecules are involved in the slow step? Only the alkyl halide. So it's an elimination unimolecular. Or E1. And again, you can write the rate law for this. Rate equals K times, now only the alkyl halide is involved in the rate determining step. So those are our two reactions. E2, elimination bimolecular, and E1, elimination unimolecular. In the E2, bond breaking and bond forming happen concerted. So E2 is concerted. E1 is stepwise. You can also draw reaction coordinate diagrams for each of these. It's going to go without any intermediates. And if I'm going to look at the stepwise one, it's going to have an intermediate along the way. Now you also may know that I do the products higher than the reactants in each case. Well, if I look at what's happening in this reaction, in the reactant, I lose 2 sigma bonds, and I replace that so I gain 1 pi bond. So in my starting material is actually higher energy at the end than it was at the beginning. Now that can be offset by the energy of the reagents and how they can be lower energy at the end than at the beginning. But in the main material, it's always going to be a little bit higher energy